Hello everyone, I'm Sher, your AEC Tech Girl, and today we're exploring the essentials of working with geometry in Dynamo for Revit. If you're interested in creating and manipulating forms and models in your project, this episode is for you. That's right, we're diving into part 4 of our Getting Started with Dynamo for Revit series, Dynamo Geometry. First things first, let's break down what we mean by geometry in Dynamo and how you can use it to create amazing designs and models. Dynamo isn't just about crunching numbers and processing text. It's also about shaping the virtual world through geometry, which is just a fancy term for the shapes and spaces you can create and manipulate on your screen. Now, what is Dynamo geometry? It is basically the language of design in the digital world. When we work with Dynamo, which has a powerful geometry engine at its heart, we unlock endless possibilities for creating precise models, automating tasks, and exploring new design iterations. Traditionally, geometry involves studying shapes, sizes, and the relationships between them. And that's exactly what we will do in today's episode. Let's get down to the basics. We need to understand the 4 basic principles of Dynamo geometry. Number 1 is geometry as data. In Dynamo, everything from a simple house model to complex architectural forms is treated as data. This means shapes are not much different from the numbers or text we have been using in the previous episodes. Number 2 is abstraction. At its core, any geometric shape in Dynamo is defined by numbers, relationships, and formulas within a space. This is what we call abstraction. When you think of a sphere, for example, you need to break it down and think about the point, curve, and values used to generate that sphere. Number 3 is the hierarchy. Geometry is all about building up. Just like in the real world, we start with the basic elements, like points, connect them to form lines, and join lines to create surfaces. And lastly, number 4 is describing part of a whole. Each geometric form, like a curve, is understood as a whole shape and as a series of points along that shape. Are you ready to dive in and start creating some geometry? In Dynamo, navigating through the library of geometry nodes might seem overwhelming because they're sorted alphabetically rather than by complexity or type. But as you get familiar with basic forms and operations, you'll become more comfortable with finding and using the right tools for your tasks. We are going to be building on the hierarchy of geometry, as I mentioned before. The first or lowest geometry of this hierarchy are points. Like I said in the last episode, if geometry is our language, then points are the alphabet. They are building blocks and simply composed of coordinate values. Within the geometry library, navigate to points, then point. This time we will create a point by coordinates x, y, and z. Let's grab some integer sliders under input and basic. We will place 3 integer sliders. Connect your integer sliders to your coordinate inputs of your point node. Play around with those sliders and watch your point move around in the background 3D view. Now that we conquered points, the next level is curves with a capital C. The term curve is a catch-all for all different types of curved shapes. Even if it's a straight or regardless of the type of curve it is, it always has a start point and end point. See how I said point? Because points are our building blocks. Back to the geometry library, under curves, we will see all options available to us. Let's start with just a line by start point, end point. I want to show you another tip to help keep your Dynamo graphs organized, and that is groups. If you drag and select a series of nodes, you can group them together by right-clicking. This makes it easier to organize and also copy groups. Let's name this group Start Point. Then we will copy it by using Control on our keyboard and renaming it to Endpoint. I'll change the number slider so that we can see both points clearly and that they have unique values. Then let's connect those points to create our line. Okay, great job. If you watched the last episode, this all should be familiar to you. Let's take it up a notch and create some different types of curves. Let's create a polycurve. Under polycurve, we will be using the by points node. Let's look at the node and see what inputs we will need, and then again work backwards to create those inputs. We know we need a series of points, and then we need a Boolean value for the other input. Let's start with our points. We already have 2 points, but let's copy these groups and make a few more points so that this curve has a bit more movement to it. We will simply copy the groups, change the group names, and then move our number sliders so that each point has a unique value. You will notice that we have now 4 outputs, but only 1 input for our poly curve. No problem. We just have to combine all these points into a list. Let's go to our list library, then generate, and we will grab the list create node. This node is very useful in situations like these where we need to combine multiple values into one input. Zoom into the node and you will see a plus and minus button on the node. Use those to add or remove inputs. We have 4 points, so we will need 4 inputs. Once we have added the 4 inputs, we can connect our 4 points to the list create inputs. We can now pin our preview below the node and see that all points are combined into one list. Then connect our list to the polycurve points input and see our polycurve being generated. If we look at the other input for connect last to first, you will see that the default value is false. But if you want to make a closed loop, you can grab a Boolean input node, change it to true, and see how your polycurve changes. Another type of curve that we can look at is a NURBS curve. The difference here is a polycurve is created using a straight line, while a NURBS curve will be created using curves. We will use the same inputs we have for the polycurve for the NURBS curve to see the difference. We will simply go to the NURBS curve sub-library and grab the by control points node. Connect the same list of points into the input of the NURBS curve. NURBS actually stand for non-uniform rational B-spline. Here's another tip. If you don't want to see a particular geometry, simply right-click on the node and turn off Preview Geometry. Feel free to play around with your number sliders and see how your curves change. As we transition from working with curves to incorporating surfaces in our models, we're stepping closer to mimicking the objects we see in the real three-dimensional world. Unlike curves, which might appear three-dimensional but are still essentially one-dimensional in nature, surfaces add another layer. They not only expand our design possibilities by adding an extra dimension, but also bring a set of properties that enhance our ability to perform more complex modeling operations. Like we have done in the past, I like to work backwards, figuring out what I want to create and then breaking it down into its inputs. Let's go to Geometry, Surfaces, NURB Surface, and grab the By Points node, as we will create a NURB surface by points. NURB surfaces are similar to NURBS curves, and you can think of them essentially as a grid of NURBS curves. You will notice 3 inputs in the node: points, U degree, and V degree. In 3D modeling, when we talk about surfaces, especially those created through methods like NURBS or subdivision surfaces, we often refer to the U domain and V domain. These terms describe the 2-dimensional parameter space that defines the surface. Think of U and V as coordinates on a grid that stretches over the surface, much like latitude and longitude on a map. U domain, this is the first parameter and can be thought of as running horizontally across the surface. You can visualize it as moving from left to right along the surface. The V domain, this is the second parameter, running vertically, and you can think of it as moving from top to bottom along the surface. U and V domain values are numbers between 1 and 3. NURB surfaces, regardless of the shape, essentially are just a rectangular grid of points. Let's create our NURBS surface inputs. We know we will need points, so let's grab a point node. I will do the quick method of searching for the node by right-clicking on the canvas, then typing the name of the node. I want points by coordinates XYZ. Let's pin down our preview to see how it changes as we add inputs. We will copy this node 2 more times to have 3 point by coordinate nodes. To show the NURBS curve, we will create a 3 by 3 grid of points. Now let's create a range. I will right-click and search for a range node. Then we will use the number nodes for our inputs for the start, end, and step. 0 for start, 20 for end, and 10 for step. Connect that to your X value of your point nodes. We have our X values. Let's focus on the Y value to create our grid. We can either use number nodes for this, or we can use one code block for all the numbers. Let's use our code block. Double click on the canvas to get your code block node, then input 0, semicolon, enter, 10, semicolon, enter, and 20, semicolon. Click on the canvas when you are done, and you will see 3 output ports created. Connect each port to one of the Y input ports of your point nodes. You should now see a 3x3 grid of points in the background 3D preview. For our Z value, let's use integer sliders so we can play around with the shape of the NURB surface. Let's set the max to 30. Copy the integer slider 3 times. This is so we can individually set the Z values of each row of points. Now connect each slider to one of the Z input ports of our point nodes. Play around with the Z number sliders and see how each row of points moves up and down. All right, now we are ready to combine all these points into a list and create our surface. Go to List, then Generate, and grab the List Create node. Add 2 more input ports and connect each output port of our 3 point nodes to the List Create node. Before we connect our list to the NURB surface, I want to point out one thing. You will notice in this node that one of the ports are red and the other are blue. Blue ports represent ports that have default values and therefore don't require inputs, while the red ports represent ports that need inputs for the node to function. Now connect it to create the NURB surface. The U degree and V degree already have a default value of 3, which you can see when you hover over the ports. So it creates a surface for us without needing to do anything else. Play around with those integer sliders for the Z value and see how your surface changes. The U and V degrees will determine how faceted the surface is. Let's create an integer slider with a min of 1 and a max of 3. Now connect it to both the U and V degree ports. See how the surface changes as you change the sliders between 1 and 3. Play around with all your sliders and watch how your surface changes. So in terms of our geometry hierarchy, we have points, then curves, then surfaces, and lastly, solids. When we aim to build more intricate models that can't be shaped from just one surface, or when we need to specify a clear volume, we enter the territory of solids and poly surfaces. Take a simple cube, for example. It requires 6 surfaces, 1 for each face to exist, right? Solids open up 2 vital concepts that aren't available with mere surfaces. One is a more detailed topological structure like faces, edges, and vertices, and the other the capability to perform Boolean operations. So what exactly is a solid? A solid is made up of 1 or more surfaces that enclose a volume through a completely closed boundary, which distinguishes them from the inside and the outside. No matter how many surfaces make up a solid, they must all connect seamlessly to form a, quote, watertight volume. You can create solids by joining multiple surfaces or poly surfaces, or through techniques such as lofting, sweeping, and revolving. Basic geometric shapes like spheres, cubes, cones, and cylinders are all examples of solids. Meanwhile, a cube missing even just one face would be considered a polysurface. While it shares some characteristics with solids, it doesn't qualify as one since it doesn't fully enclose a volume. For this example, I thought it would be fun to create a Lego. Don't worry, it won't be anything crazy. We will just create a simple Lego block. This here will be our inspiration. When looking at this Lego piece, we will break it down into 2 essential parts, the main body, which is a cube, and the cylinders that sit on top. Let's get started. Go to the geometry library, then solids. We are starting with the main cube body. So go to cuboid, and we will use the by corners node. This will allow us to use points to set our size of our cube. Let's now get 2 point nodes. For the low point, we will leave it with the default values of 0, 0, 0, and just connect it to the low point port of our cuboid. But for the high point, this is where we will specify the size of our cube. Get 2 number nodes and a number slider. For the width, we will set 20, length will be 40, and for our number slider, let's do a max of 30 for now and input 10. We created our cube. Let's make sure to keep this graph organized and create a group and name it Create Cube. For now, let's turn off the preview of our points. Next, let's create the cylinders that sit on top of our cube. Back to Geometry, Solids, then Cylinders, we will create a cylinder by points radius. So we know we will need some points. Let's start by creating our points. They will start at the top of our cube, so we already know we can use the same z value. Now we have to do some math here. Essentially, we will have 6 cylinders on top of our cube per our Lego design, and those are evenly distributed. We will have to do a bit of math here since we know that we are actually not starting the distribution from the edge, but at a distance that is half the value of the distribution value. Let's grab a range, and to make it easier, I will simply use a code block to do my math. I want to base this off the cube's x value, so we will use x in our equation. Let's start with our step. We know we will have 2 rows of values, so let's just do x divided by 2 in our code block. Connect the x value to the code block, and then connect the code block to the step input. For the n value, we can simply use the original x value. And for the y, we will grab a code block and input the equation s minus s divided by 2, s being our value for our step. Connect the s value and then connect the code block to our start value. Now let's do something similar for our y values. Let's copy and make changes. We will change the x to y. In this case, we are dividing by 4, so change our step to y divided by 4. Connect our y range to our points. You won't see a grid of points just yet, but if you remember from our previous episode, we just have to change our lacing. Let's update our lacing for our points node from auto to cross product. Now you will see our grid of points. That just got us our start points for our cylinders, but we still need to create our endpoints. We will need to copy these points up so that we can determine how high our cylinders are. In Dynamo, copying geometry is referred to as translating. Let's go to Geometry, Modifiers, Geometry, and here you will see all the ways to modify your geometry. We need to find the translate direction and distance. We have 3 inputs we need to create. One is geometry. This will be those points, so you can connect our points to this port. For direction, you will see when we hover over the port that it requires a vector. Now, a vector is a geometric quantity for describing direction and magnitude. Vectors are abstract, meaning they represent a quantity, not a geometrical element. Within our geometry library, we can go to abstract, then vector. We will grab the z-axis vector. Then for distance, let's use a number slider. Let's do a min of 1 and a max of 10 and connect it to the distance port. Amazing. Now we have our start points and our end points. We can now connect those to our cylinder node. For the radius, we will again just use a number slider. Let's set the min to 1 and the max to 5. Look at that. We are on our way to creating our Lego. We still have a few more steps. Let's group these as well to keep it organized, and I will hide the points again. With solids, we can perform different operations on them, like Boolean operations to intersect, split, delete, or join them. Let's join these geometries into one. Go to Geometry, Solids, Solid, and then we will union the 2 geometries, which means joining these 2 solids together. Now connect the cuboid and cylinders into the union node and see how they combine into one solid. Let's now hide the separate previews. Now you can go ahead and play around with those number sliders and see how our little Lego-inspired geometry changes. Wow, look at how far we've come. We've just scratched the surface of what's possible with geometry in Dynamo, from the basics of points and lines to creating complex surfaces and even starting to explore solids. I hope you found this tutorial helpful and that it sparks your imagination for what you can achieve in your own projects. If you enjoyed this episode on Dynamo Geometry and want to keep building your skills, make sure to hit that like button, subscribe, and ring the bell for more updates. creates. Leave a comment down below of some geometry you have made using Dynamo. Thanks for watching, and remember, stay empowered, stay inspired, and always challenge what is possible.